In this short webinar, I would like to show you the conclusion and the usable materials that were recently published and shared among the community regarding the CEN workshop agreement 17815 on materials characterization, terminology, and structured documentation. So this is a tool that is publicly available and mostly is giving any scientist a common language and a formal approach on how to structure and report the characterization data. And this started from a previous CWA that we delivered in 2021, in which we introduced the concept of CHADA. CHADA means characterization data. And at that time, we simply presented and proposed a way that was based on the combination of a workflow, which is what you see on the left, and a series of documentation tables, which is what you see on the right. So it was very nice because we were able to discuss on the terminology, on all the keywords, how the data should be structured, what would be the necessary information to be included in the data. Everything with only one main objective, which is to have a full documentation of the data so that anybody can recover and retrieve the information on, and so to improve the fairness of the data. So next slide, please. This was the time frame. So we started almost a year ago within the project Nanome Commons. So that is why you see Nanome Commons logo in these slides. But that was practically supported fully by the European Materials Modeling Council and the European Materials Characterization Council. And the CEN workshop was started almost a year ago and now is completed. And the document that you see on the bottom right is available online. So you can simply, but probably someone will put in the chat all the links during my presentation on how to download and how to use the document. In parallel, we also already published a couple of case studies. So case studies on how in practice to use this tool. The main difference between the previous CWA and the new CWA is the following. In the previous one, we only gave conceptual ideas. In this new version, we also give tools to develop the ontologies, tools to develop the workflow diagrams, and tools to make everything more interoperable and automated. Okay, so if you go to next slide, I think from now on, Eduardo can take the speech and the word to discuss what mostly we did. Again, I say once more, this is the work done not only in Nanome Commons. It was founded by Nanome Commons, but it was supported by the European Materials Modeling and Characterization Council, and also nowadays is included in the current actions within the new materials partnership that is ongoing. Thanks, Eduardo. Please, sure. You can move on.
So the main, let's say, improvement with respect to the previous CWA, as Marco was saying, is that now in this CWA, we implemented a so-called ontology. Very briefly, what is an ontology? An ontology is a model that defines concepts, their properties, and how they relate to each other. So this is very important to have a structured data and to define a characterization workflow and characterization data, so the CHADA. In this case, we're speaking about a particular kind of ontology, which is called characterization methodology ontology. It translates in the acronym CAMEO. And CAMEO is exactly a framework that defines clearly machine-readable documentation for characterization experiments. So it's that simple, and this is how it comes. And you see on the right, there is a diagram saying that basically every use case, so this diagram must be read from the bottom to the top. Each use case, which was the examples that Marco was speaking about, import a specific low-level ontology, which in this case is the nano-indentation ontology. So again, a framework that defines in a machine-readable way what is a nano-indentation characterization experiments. And on top of that, there is the high-level ontology, which is the so-called Cameo. So Cameo encloses all the high-level concepts that are needed to define a characterization experiments. So the main takeout message of this slide is that in the new CWA, everything will be enclosed by clear and specific machine-readable documentations, which are defined by Cameo. So let me skip that one. So in Cameo, we have two main examples of how things are defined. So if we start from the material or batch we have to characterize, we can see clearly that we have some preliminary metadata which have been defined, which are the dimension, the structure, the materials, physical and chemical composition, the hazard. So we have to be compliant also in that field. And you can see that the characterization procedure is eventually composed by the sample extraction, the sample preparation, and the sample inspection. So this gives you the framework by which we can pass from the material or the batch to our sample. Then again, a measurement must be done with instrument that is calibrated. So we need to enclose concepts and definition for the calibration process, the measurement system adjustment, and the characterization measurement process itself. So all the definitions of what we are doing on our sample to extract the data. And then, of course, we have the final step, which is probably the most important step along with the characterization measurement process, which is the data preparation, the data post-processing, and the data validation. All these 9 characterization procedure steps give us the final output, which is the characterization data that now is clearly composed by the calibration data, the raw data, the so-called primary data, which are eventually parts of the raw data that are crucially needed to define our properties. Then we have the secondary data, which is parts of the raw data that allow the user to interpret a little bit with more precision the primary data output. And then we have finally the characterization property, which is our, let's say, final aim to be defined. This involves all the aspect of, let's say, the classical agents, let's say, of the ontology, which are operator, laboratory, instrument, environment, and parameters. And then also, and this is really important, and it's a novelty of this ontology, which is the level of expertise, because you can imagine that each, let's say, raw data interpretation, and so each translation from the raw data to the primary data needs a level of expertise to accompany that metadata, because we need to understand who was the user and which level of interpretation it has made on the data itself. So is a flexible, as being a high-level ontology, this is a flexible framework. So we can interpret and we can define various steps of our sample characterization. So we have, as an example here, we have all the levels of details a user can go through from the material batch to the calibration data and to the final data. So we have the sample extraction, we have the sample preparation. So we define a raw sample, which is the extracted sample, and then we define the prepared sample through the sample preparation. And then we have, from the reference sample, the calibration process that gives us the calibration data. So all the workflow, which is enclosed in the Cameo ontology, will be basically what is written in the right hand side of the diagram. So from the material batch through all the steps of sample extraction, preparation, inspection, through the calibration toward the data post-processing that gives us the extraction of the secondary data and the primary data. Okay, so basically this is all what is enclosed in the Cameo ontology. Let's have a in-depth, let's say, vision of an example of non-indentation calibration process, so you can understand really what are the steps into these characterization diagrams. So our reference sample in this case for non-indentation would be the fused quartz or fused silica sample. We have in the non-indentation calibration process several steps that are being defined. So remember that every time I'm presenting this data, I'm speaking about something that has been enclosed in a framework that is machine readable, and so everything is defined, everything is clearly stated, and you have a list. You will see after this example, you have a list of parameters which the user must fill to complete all the metadata and the characterization process. So we have, as an example, the microscope to indenter calibration, so position calibration of our indent, tip area function definition, compliance calibration, so this is our frame stiffness compliance. Then we have the measurement itself, which is in this case continuous stiffness measurement, and we go to the calibration data. Again, the continuous stiffness measurement with a higher granularity, so we speak about granularity, and we mean that every definition itself can be expanded to several other sub-definitions. In the continuous stiffness measurement, we have all the steps to acquire the data with the CSM, the so-called CSM mode. So you may ask yourself, okay, but now that we're speaking about ontologies, how we can clearly define the terms within the ontology? So to define the terms within an ontology, we need what is called as taxonomy. So there is a distinction between the ontology itself that encompasses all the machine-readable concepts and their relations. And then within the ontology, we have the taxonomy. So the taxonomy is a series of standard nomenclatures that define all the high-level frameworks of the ontology itself. So you see here there is an example of the taxonomy for various characterization techniques we have enclosed in this CWA update action. So you can see that in the microscopy, as an example, we have defined atomic force microscopy, confocal microscopy. It may seem to a, let's say, expert user something obvious, but it's not, because when you go to higher granularities, and when we speak about, as an example, elastic modulus, some users may use the term Young modulus, some others may prefer the term elastic modulus, but we define the correct term, which is elastic modulus if we're speaking about non-indentation. So we really need some highly accepted terminology to be used with our ontology. This is the Cameo structure, nothing very, let's say, important in depth to say, but this is what it appears to be an ontology at the end of the story. So when you have defined what you need, so the definitions you need, and the terms, the terminology you need to use. So you can see that, as an example, we have that the task of measurement as an operator, the definition of the operator, so the Cameo definition of the operator, and this is compliant with the EMMO ontology, in which the operator is defined as an intentional agent. Again, the task as a laboratory associated, the task as a characterization workflow associated, and the characterization workflow as a characterization procedure. So this is how an ontology with the terminology associated works. So let's say let's get a little bit more in depth. So the characterization task has a begin step, an end step, internal steps or iterative steps, and then it can be even serial. So you can define in the ontology all the aspects that define the workflow in its shape. So not just terminologies and definition, but also the shape of the characterization flow. You can say if it's parallel, serial, whatever. And then these will be translated, we will see it in a while, into a clear workflow diagram that in the new CWA, it has also been standardized. So in the simplified non-indentation calibration process, so what the workflow, the diagram workflow that I've shown you in the ontology, this is how it is translated in the Cameo ontology with the proper taxonomy. So you have the characterization task. Part of it is the microscope to indenter calibration. Part of it, of course, are the properties of the reference sample and the non-indenter itself, so the characterization instrument for Cameo and the reference sample again for Cameo. And then you have that this task as a measurement as the continuous stiffness measurement, which is a non-indentation measurement, and for Cameo is a characterization measurement process. This continuous stiffness measurement has output the load, as output the displacement, as output the drift rate. So all the properties have been categorized and inserted within the ontology itself. Let's go fast on that. So to design any new ontology, you basically need these 8 steps. So you have to define the scope of your ontology, so documentation, why and how the ontology is inserted within a specific field. You have to analyze the existing data, so you have to collect all the possible data within the characterization field you want to ontologize, and you have to understand how this data comes from different instruments, different, let's say, actors of the measurement itself. You have to define the so-called competency questions. Competency questions are a list of, it's a questionnaire basically in which you define each property and each definition of the ontology, which actors and which, let's say, framework it has to have. Then you have to create the so-called glossary and taxonomy. Again, we need standard terminologies to comply with the ontology itself. And then you have to create specific diagrams. So the BPMN diagrams are process diagrams which have been standardized. Those are available with a software called Camunda. So we're not using any, let's say, arbitrary diagram itself, but we want to use a diagram in which the shapes, the colors, and the relationships are clearly defined, and those, let's say, figures have a ontology themselves to define what you have to use and how you have to use it. So you don't want to go out of the standards with that. And then you start developing your ontology. So you start developing the relations between the definitions, and you start to associate to the definitions what are the terminologies coming with. The ontology formalization is a document in which you write down all the relationships and all the terminologies, and then you create the final instances, which are, let me go back on the slide, which are those kind of diagrams in which you define everything and all the relationships within the whole field of the ontology itself. This is done by a software which is called Protégé, in which you can define all the entries of an ontology and the taxonomy associated, and then you give these terms the specific relationships. So at the end, Cameo reached a fair score of 100%. So it's findable, accessible, interoperable, and reusable. There are specific templates. We will see it declined on our let's say new CWA format. As Marco was saying, we have done intense use case definitions, mainly on non-indentation testing and focused ion beam digital image correlation, and we applied it to use cases from several industrial partners in Nanome Commons project. So this is an example again. This was an example of ontologization of the process in failure testing for multi-layered coatings. So again, it's an application of non-indentation to the specific output property, which is the failure resistance of coatings. You may see again that we have the reference sample, which is our polymeric material. Then you have as the main, let's say, characterization task. So this temporary participant, which is the polymeric material as a reference sample, as the task, which is non-indentation. And then this task is defined as a characterization technique. Let's go to the very, let's say, core of what you need. This is a BPMN diagram example from high-speed non-indentation mapping. So in high-speed non-indentation mapping, you acquire thousands of data points mapping the surface with a non-indenter. So the outcome is a map of the hardness and the elastic modulus. And you may see that in our BPMN diagram, we have defined, this is the begin task marker in a BPMN diagram. This is the end task marker. And we have all the steps you need to define for the high-speed continuous stiffness measurement. So the definition of input parameters, you have definition of either the target displacement or the load of your indenter, and then you go to the selection of the dynamic parameters, so strain rate, dynamic displacement, frequencies. You pass through the test execution. Again, you have the start of the test and the end of the test and all the steps in the test execution. And then you come out with your raw data, drift rate and load displacement data. You apply the correction defined by the method, and these green boxes, actually, with following a specific color code, are the boxes corresponding to your raw final data. Again, the BPMN can represent all the characterization tasks themselves. So you have the representation of the sample preparation, the sample inspection, different boxes for them. All the boxes have the start task and the end task. Then you have the output of one box comes as an input of another box. Calibration, measurement, and post-processing. The final aim is to get into the final, let's say, characterization properties themselves. This is a very big example of the ontology for an MO-based ontology for batteries. So you may have understood right now that all these steps require a lot of efforts and they are a lot complex depending on the granularity you want to give to the use case you are analyzing. So this was a battery testing use case from Keysight, and you see that all the terminologies, all the actions, and all the participants as materials and as users have been defined in this huge diagram that is basically the ontology for battery itself. So you have definitions, you have terminologies, and you have relationships. So to maintain and develop an ontology, this is the last step toward, let's say, our example, you basically have to pick up a use case. You have to define a rationale on your use case. The rationale is basically why you are using a specific characterization for the specific use case you are analyzing. So let's say that we have a coating and you have to test the durability. The rationale will be why, as an example, we are using the pin on disk to characterize the durability of this specific coating. The rationale defines also the characterization workflow, because when you have defined what is your testing methodology, then you can define, it can be multiple, you can define what is your workflow itself. So scanning electron microscopy if you want to see what is the surface like, nanoscratch if you want to understand what is the adhesion and what is the failure, the cohesive failure of the coating itself, and then the surface-free energy if you need also to characterize. This was an example on biocidal and bactericidal coating, so you have to understand how the surface itself is prone to adhesion with other materials. So here you see that we have defined in the rationale and all the steps is what is needed to be written in the ontology. And a use case, and this is to tell you a really important thing about ontology, a use case can have multiple rationales. So I was giving you the example of pin on disk, and then in the slide it was written SEM, nanoscratch, and surface-free energy measurement. This is because a specific user or a specific intent can be declined in, it can be, let's say, divided in several ways to reach the characterization property you need. So it's not mandatory to have a single use case and then have a single rationale. You can define multiple rationales to that. You have a series of reviews and documents you can consult to understand better what is an ontology and what is a taxonomy. So maybe this one will be a reference to go in depth on the concepts I'm saying. Very briefly, what we do in Roma 3. So in Roma 3, we decided to implement this ontology with specific, like, very defined and how you say, like, specific and robust steps in which we're using software and a combination of data logging, because the worst case scenario you would like to do is after you have defined an ontology and the related taxonomy, you are not using it. So you need something that translates your ontology into real logging and metadata collection steps. To do that, we do sample logging, sample preparation. We do the measurement process in a software which is called eLab, and I will briefly go through that in the sake of shortening the presentation. So for the sample logging, we're using as an example SharePoint tables in which we have specific codes for each sample. To define the process, we have a software which is called eLab FTW, in which you can insert the metadata of all your characterization. This software has specific templates in which the taxonomy is already defined and you can fill in via software. So this is very important. This is, you can also define the operational environment. You can define the instrument. And to conclude, this is the final output of the new CWA. So Cameo ontology, Camunda for the BPMN diagram. This is an example. And then you have tables with clear definitions and clear tabular data to insert for the characterization workflow, from the sample extraction to the final results analysis. So those are all terminologies which you find in the ontology. Okay, so takeout messages, and I'm closing this quite long presentation. Sample logging must be digitalized, and a secure identification of the information must be done. The full experimental practices must be implemented in electronic lab books. We are using eLab FTW. And then the entire characterization protocol must be compliant with the CHADA forms and the Cameo ontology from the new CWA action.